So applications of centripetal force, I left this last example as a lead-in to the banked curve. This question is talking about specifically a level curve. So it just means you've got a highway curve, and actually this rarely happens, that you have a highway curve that doesn't have a little bit of banking to it. But imagine that you did, completely level, no banking, and say it's got a speed of 22, what's that? 22 times 4, about 80 kilometers per hour, okay? And we know the radius of the curve, and just because, just to give you an idea on a curve here, I mean, it's not like it's a circle, but it still has a radius, so you would figure out sort of the distance from, if you drew it with your little compass, what the radius would be. So first it asks us to draw the free body diagram and name the force that provides the centripetal acceleration. You might be already copying this. Excuse me, I can't remember. You might even have it on your note already. Part B, we want to, once we know what that force is, we want to calculate it. Magnitude, mean number. So what is the number value of that force that must be exerted to keep the car from skidding? Because the idea is, if you've ever driven on a highway, again, just like anything else, there's something that keeps you would just, your car wants to go on a straight line. Something causes it to turn, right? And to stay on the circular path. And you're thinking, well, it's my steering wheel that causes it to turn. But there's something that has to be present, otherwise it would not turn. And that something is, of course, friction. And really, it's a static friction. We haven't talked about this much, but static friction that propels a car forward. And in this case, it's static friction, the fact that your car's not sliding on that level curve, that forces it to turn around the corner. And we're basically going to use the information of this speed and a highway curve of this radius to calculate what the static friction has to be on your car tires so that you don't slide off the curve, right? So just as you have the free, this isn't really a free body diagram. Well, it is from the top view. You can only see one force. And then if you're looking from behind at your vehicle, so here's my car driving into the, driving forward, I'm looking back and normal up. And FC, the centripetal force, is, like I said, it's friction. So just looking to the calculation then, well, all you really do is you say, well, if FC is equal to my static friction, then I can calculate static friction because it's mass times centripetal acceleration, use the formula for centripetal acceleration, and solve for Fs, knowing the mass is given, the speed of the car, and the radius divided by 85. Notice, by the way, that in this case, the mass of the car makes a difference. And when you think about, well, there's a bunch of things, but, a heavier car helps you from sliding off the road in a case like this. Okay, so then if we're looking for coefficient friction, then it is just simply a grade 11 problem where we know Fs is this, Fn you just calculate to be mg, just looking at the free body diagram here. And the normal force then is just 10,780. And so when you find coefficient of friction, you substitute here into here, and you solve for Fs. And we know that a good number, or μs, sorry, a good number from us is always between 0 and 1. Okay? So that's our first example, and of course I hope that you've paused to keep up with me, and I'm just going to move on straight into the description of the banked curve, which is really today's lesson. And here we go. Okay, so the bank curve, and you may have realized this is nice. This is the best picture of it I can think of as having, it's just on a racetrack. It's an exaggeration. You can see the banking angle really well. You can't always see it that well when you're on a highway, but all highways do have one. And notice now when you're driving, notice them, okay? And really, the reason is we want to keep this, this car here, from flying off the highway. Well, what keeps it from flying off? Well, it's the curve itself, the presence of the curve, which means it's the normal force, keeping you on the highway. So it's a component of normal. And if you just took a look here, and if I was going to draw towards the center of the circle, I might draw something like this, right? And that looks like, basically, if I knew this angle here, it would be like the x component, so to speak, of my normal, something like that, right? That's the component towards the center of my circle, and that's what's providing my centripetal force. Okay, so I'm just going to we're going to come up with some formulas using the free body diagram on a car such as this, on a banked curve. And how we solve in the grade 12 course is no friction. We always assume no friction. Basically, I give you some nice formulas that work and no friction, and that's an okay thing to do, because most highways are designed so that it's a totally icy day, you still don't fly off the road, right? Assuming you're under the speed limit or whatever. Okay, so that's really probably how an engineer would design the road, would assuming that there was no friction. So if a hydroplane or whether there's black ice, whatever, you're still going to stay on the highway. So it's not that silly to come up with that. I do have a bonus, we'll talk about it after, to find out the answer to our example problem later on, using pretending there was a coefficient of friction, and it's hard. It's a great bonus. You will earn your bonus mark if you can do that. Anyway, moving on. So just looking at the banked curve free body diagram, again, this is pretend my car here is driving into the page, okay? And so I'm looking at the bank from the side, and again, there's normal, there's gravity, and the center of my circle is over here somewhere, right? And that's got to be, it's not going to be a component of gravity because it's completely perpendicular to gravity. So the component of normal, that's going to be the centripetal force, and is going to be over here. And because it's completely perpendicular to gravity, it's not, while normal force is a component of gravity, this is only a component of normal, which sounds confusing, but just give me some time to come up with a nice easy formula, and you'll forgive me for that. Okay? Again, just looking at the top view, this is what you're seeing. The car is moving around this way, centripetal force towards the center of the circle. And this is, I should make a note here. Looks a lot like an inclined plane, but it is different. And one thing that makes it different, and I don't think I did a good job here, is that really the normal force is greater than gravity on an inclined plane, and you can almost, on a bank curve. And if you just put yourself in the position of being on a bank curve, and you can almost feel, you get the feeling of being sort of sucked into the ground. Well, that's pressure, that's normal force, right? And our analysis has to be different here. So just moving on. So if I was going to look at, the components of normal, and I just decide to draw them, like usually I draw the triangle where this would be right here, right? And that's definitely true, but for the sake of making everything look balanced, up and down and side to side, I drew it to over here. So let's look at everything. If I look at, and notice, here's a big thing you should bring your attention to, right here. Unlike the inclined plane, where we say that that positive y direction is perpendicular to the like it'd be the same direction as normal, and then the positive x direction is down the incline. On a bank curve, we keep the normal reference system where up is y and horizontal is x. Okay. So just some things here to take a look at. If I'm doing a force balance in this up-down direction, I say that, notice, maybe I should just highlight this here. So here's our angle, our banking angle. That's what you would call that, okay? And just looking at a Z law, this would be equal to it as well, right here. And that would make this equal 90 minus it, which would make that equal to theta. And if you don't follow that, take a few seconds to look at it, and you'll see it yourself. It's not a huge deal anyway, just if you trust me on it. Then you can trust that this component right here is normal times cos of this angle, because it's touching the angle, okay? And because I'm doing my force balance in this direction, then I've got this Fn cos theta has to be equal to mg, right? Fn cos theta is going to be mass times 9.8. I'm looking at the x direction. Now, this is Fn sine theta right here. And if you're wondering why, again, if I put, whoopsie, that wasn't what I meant to do. If I grabbed my vector here and brought it up here, you could see that it should be equal to, it's opposite to theta. So this, what I call the centripetal force, is equal to Fn sine theta. So then, if I just take a look right here, I can say Fc, which is F and sine theta, over Fg, which is Fn cos theta, right, is equal to the ratio right there. So all I'm doing is sort of putting this together to come up with an equation. And the equation is quite nice. Because sine theta over cos theta is tan theta, then I can say my centripetal force divided by gravity, which is just mg, equals tan theta. And that is the formula for dealing with banked curves. And if you write that down on your sheet, you know Fg is always mg, you know that Fc is always mv squared over r, or involving period in these questions, always mv squared over r. You can simplify that even further. Okay, so that is the guiding equation for banked curves, because we assuming no friction. Okay, and we do assume no friction. So just looking at this again, here's our guiding equation, like I said, and yeah, we're going to apply that. I'm going to make another video just with the application of that, and it looks hard. Banked curves look like they're hard, but if you just bring it back to this equation right here, it's actually kind of easy. Let's see the example in the next video.